Hi everyone, it's Juan here. In this video, I'm gonna show you one of my favorite features in TornadoVM, which is the ability to run an application, a Java program, on multiple hardware accelerators and with multiple backends, even concurrently. I'm gonna illustrate these concepts through two applications. The first one, I'm gonna have a client-server application in which the client is gonna set the device to run in the server dynamically. And we're gonna even run it with different backends. The second application is about computational photography. We're gonna take an input JPEG image and produce several images. Each image has a filter, and we are gonna process this in parallel with multiple hardware accelerators and multiple backends. Sounds exciting, doesn't it? Let's do it.
Before we dive into the examples, I'm going to show you the TornadoVM configuration and the setup I'm using. So I already configured the machine and the TornadoVM environment to use all backends that TornadoVM supports, which are the OpenCL backend, the PTX backend, and the SPV backend. So if you wonder how to configure TornadoVM, I made a video recently explaining the setup for different operating systems and different configurations, backend configurations. So I want to put a link in the description down below in the case you need to check that first. But in a nutshell, once you configure Tornado, you can recompile with different configurations, and you just type make, and then you select backend equal, and then you select the ones you're interested. So in my case, I'm gonna open the OpenCL one, SPV, and the PTX. So we run. It will recompile the whole project, and if there is a missing dependency, it will download and install that dependency for you. It will take a few seconds. We wait until the process is finished, and then we check the devices that we can see in the current instance of the TornadoVM runtime. So almost there, done. So let me clean the screen. And if I type tornado -- devices, then I can see a bunch of devices that TornadoVM can access. So each backend is identified by a color, different color. So in the case of SPV is the purple color, OpenCL is the blue, light blue, and the PTX is green. So the ordering that you will see if you run this in your system might be different, because that depends on the devices that you have and the backends that you enable. So by default, Tornado access the device 00. That's the way to identify devices, and that's important for this tutorial because we're gonna change based on this index. What the index means is backend index colon device index. Backend index in this case is 0, SPV. Device index is 0. For the backend index 1, in my case, is OpenCL. Device 0 within that backend is the RTX 3070, and device 1 is the Intel Integrated Graphics. This is the same as this one, but you can access from different backends, which is quite interesting. And the last backend is a PTX, is a CUDA PTX with the RTX 3070. Again, this is the same device as this one, but accessible from different backends. I'm gonna go a step further. I'm gonna enable the OneAPI toolkit to access the Intel CPU as an accelerator. So if you want to run Tornado on CPUs, you can do so. One way to get that is through Intel OneAPI toolkit. I already download and install the toolkit, and the way to enable it, at least in Linux, is to set up the environment through the source file. So it's in OPT by default, Intel, and then OneAPI, and set bars. And done. We don't need to recompile Tornado whatsoever. We just type devices again. And now we see we have more devices than before. So for the SPV, nothing changes. For the OpenCL, we have the same RTX 3070, the integrated graphics, and an Intel CPU through the OpenCL. And the index now is 1, 2. We can also access an FPGA. In this case, it's 1, 3. For this tutorial, we're not gonna use the FPGA because in the case of Tornado, we need to enable some extra configuration. But in the future, if it's something that you want to see, just leave a comment in the down below, and yeah, I will try to make to do a tutorial. And the last one is the PTX RTX 3070. Nothing changes on that regards. So again, we're gonna play with the indexes. I'm gonna keep a tab with this configuration, and then we will move, we will change the device based on these indexes. So with that out of the way, with this configuration out of the way, let's jump now to the description of the server client or client server application and the execution, the demo. So this is the workflow of the application, very high level of the workflow of the application we want to achieve. And we have two components. We have the server application, the server process in Java, and the client process. So the goal, again, is to dynamically switch device at runtime, and the device could be from different backends, from different technologies. For example, from one SPV device to one OpenCL or PTX device, back and forth, as many times as we want. So the way to do this is that the server already has a pre-built task graph and execution plan. By the way, in the previous video, I explained in detail the programming model. So if you don't know what a task graph is in TornadoVM or an execution plan is, I will refer to that video if you want to get all details. So the server has access to the task graph and execution plan, and is the one that will run on the device. The client will just be prompted to select a device, send that request to the server, and the device to select is given by the client, essentially. So the workflow is as follows. We start the server, okay, we configure the server, and we wait until a client connects. The client will connect, will accept the request, and send a notification that everything is ready. So the client will be prompted with, select device, please. The client will select, for example, device 0. Send a request to the server. The server will parse the message. It's given in a string format, so we will have to parse the message. It's a very simple process. Then the server will change device, run it on the selected one. In this case, it's 0. Let's say that this part here is 3210 is the number of accelerators. 0 could be a GPU, 1 could be an integrated GPU, 2 could be the CPU, and so on and so forth. You get the idea. And then the server will wait until the application on the accelerator finishes and sends a new notification back to the client to prompt with a new device. This process repeats until the client disconnects. So with that, let's take a quick look to the source code, and then we'll jump into the execution. So this is the source code. All examples I'm gonna explain in this tutorial are available on GitHub. I'm gonna put a link down below in the description, so it's easy for you to follow, or if you want to test afterwards. So we have a package called task migration, and we have two classes, server class and client class. Let's focus on the server one. So the server, the constructor, what we'll do is to create a task graph. We'll have the data, we'll allocate the data, and we will have a task graph. The computation in this case is very simple. It's just for the demo. It's just a vector addition. So it takes two arrays and then performs value plus value from the same array from the first input. So we have to copy in the input array and copy out the output array. And in between we have the task. Okay. So that's the task graph definition. And then from there we build the execution plan. But in the constructor, we don't run anything. We don't run the execution plan, because to run, we need to change the device, and the device is given by the client request. So if we go to the run method, this is a thread, okay, that will run in a loop. So it will establish the connection, and then it will try to get the message from the client, from the request, client request. We'll parse the message over here. Here is a check just to be sure that the request doesn't, the device that is requested, okay, is available in the system. We have that index available in the system. You can ignore this for this demo. And this one here, we select the actual device. So Tornado has a factory method within the class Tornado execution plan The factory method is getDevice. We touched a bit on this in the last video, in which I explained the TornadoVM programming model, but here we will expand with more details. So this method receives two arguments, backend index and device index, and those are the indexes that we were talking before. From there, we get an instance of the device, and then we change the device using the execution plan. So execution plan dot with device, and then we pass it the device we want. The interesting part, the device could be from any backend. As soon as the indexes exist in the TornadoVM runtime, that's fine. It will switch the device, and then it will execute the program. Let's take a quick look at the client application. It's very simple, just for the demo. So it will establish the connection with the server over here, and then it will run in a loop, sending requests to the server. So with that, let's jump into the demo. So for the demo, I'm gonna use tmux because I need two terminals. So I'm gonna split this into two. So on the left-hand side, I'm gonna run the server application, but I need to set up the environment again for Tornado. So yes, I need to set up the environment for one API to access the CPU. That's easy. I can do opt intel one API set vars, done. And if I do this, I can see the Intel CPU as well, along with the other devices. So, okay, perfect. So on the left-hand side, I'm gonna run the server. On the right-hand side, I'm gonna run the client. So let's start running the server. It's ready. So now we can run the client application on the left-hand side. The connection is established, and now we can select a device. So let's go to the list of devices. So if I type again tornado-devices, let's start with, I don't know, for example, this one, Intel Integrated Graphics. So it's 1:1. So let's do that, 1:1. And we can see the code and we can see the debug message. This is because I run the script with debugging information. Okay, you can see in the script all these flags. I'll also explain in the last video how to get this information. Basically, we run with print threads, so thread info, and print kernel to see the generated kernel. This is interesting because depending on the technology you use, depending on the backend you use, you will see different code. This is OpenCL. You don't have to go to that detail, but this is OpenCL, and that makes sense. We select 1:1, which is OpenCL, on the Intel Integrated Graphics. Is it? Intel Integrated Graphics. Great. Now let's go back to our list. Let's jump to 0, for example. This is PV on the Intel Integrated Graphics. Let's do that. So it's 0:0. Great. This is disassembled PV code. You don't have to go to that detail, but it's good to see that this is actually the one selected. And the backend selected was SPV on the Intel Integrated Graphics. That's awesome. Now let's go to the CPU, 1:2, for example. If you go to 1:2, again, it's OpenCL, okay, and selects the CPU, and that's the number of threads. If you pay attention to the number of threads, in this case it's 20. This is because this CPU has 20 cores. So Tornado adjusts to the maximum number of cores per device, let's say. Actually depends on the application and depends on the input data, etc. So now if we jump back to, let's say, 0:0 from here, now we don't see the code being generated. This is because the code was already compiled. So it's a code cache. So it just runs in the device. Now let's do one more test. Let's try to get the code on the NVIDIA again, RTX 3070, using the PTX backend. So if we go there, so it's 2:0 index. Right, this is PTX code, assembly code, and that's the device NVIDIA RTX 3070 GPU and the number of threads to deploy. That's awesome. And we can, go back and forth. We now select the NVIDIA through the OpenCL, 1:1, 1:2, 0:0, 2:0. Okay, you get the idea. So basically what we're doing here is at runtime, without restarting the application, the server is switching devices not just within the same backend, but across different backends. And this is great. This is a unique feature of TornadoVM. So with that, let's jump now to the second demo, in which we will show the potential to run multiple tasks on multiple accelerators concurrently. Now I'm gonna show you a second application in which we're gonna play with image processing. Okay, I call it multi-image processing. Basically, from an input image, we're gonna create two images. The input image is a color image, it's a JPEG image. We will process this with Tornado, and we will create two images. One with a blur effect, basically it's a blur, typically filter found in Instagram or Zoom meetings, these kind of things. And the second image is a black and white image from the original version. So to do that, let's go a bit in detail. So we're gonna create a task graph with multiple tasks. Each task will process different part of the image or different workflow of the image, let's say. So we're gonna use the first task for processing the black and white. So the input for this task is the original image, and then we will convert it to black and white, and that will correspond with the output. For the blur effect, we're gonna divide the image in 3 channels. So it's gonna be a JPEG image. We can represent that JPEG image with RGB, okay, red, green, blue channels. So we are gonna convert the original image into to extract the channels, and each task is gonna process the blur effect per channel. So we're gonna process the blur effect for the red channel, for the green channel, or for the blue channel, and then combine them afterwards in a single image. And then we have a color image with this blur effect applied. So with that, let's jump into the code and show you how you can use multiple accelerators. So now I'm gonna open the demo project. Again, this is linked in the description down below. So if I open this multi-image processor, that's the one that I'm gonna use. And I'm not gonna show the internal parts for each task, for each computation. For example, this is for the black and white transformation. This is a convolution for processing the blur effect, etc. You can read that in the code on GitHub. Where I'm more interested is in showing you how you can select multiple devices. So as I say, we have a task graph with 4 tasks. This is the input and output data for each task. And the first one, as we described, is gonna be dedicated to the black and white filter. And then the second, third, and fourth task are gonna be dedicated to the blur effect for the red, green, and blue channels. So we have a task graph with multiple tasks in it. We create the execution plan from the immutable task graph. Remember this from the last tutorial in which we explained the TornadoVM programming model in detail. And then how can we select different devices? Well, there are a few possibilities. So if we do as we did for the client and server application, we can do this call with device, and then no grid scheduler, this one with device, and then pass a device in here. And this device selected using the call that I explained before. For example, device 00 or 10, whatever it is. Okay. What's gonna happen is that if we do that, all tasks that belong to the same task graph are gonna be executed on the same device. But we don't want that in this example. What we want to explore is to run each task on a different device. How can we do that? Well, from TornadoVM 1.0, there is a new API. It's a variant of the with device. It's called with device. You pass an identifier and the device to select. How do we know the identifier? Well, we already give names to the task graph when we build it. So the task graph, we call it image processor, and then each task is named black and white, blue, red, blue, green, and blue. So let's say the first task, we want to execute it on the Intel integrated graphics. Okay, so we select device 00. This is tied to my configuration. So remember, if I bring my configuration side by side over here, so the device 00 is the SPV, okay, device 10 is the RTX 3070, and so on and so forth. So I did a mapping here for us, easy, to be easier to follow for this example. So if we want to select the device 0 for this task, we just type device 0. And then we can select this one, RTX 3070, we select device 1. This one is for the device Intel integrated graphics with OpenCL, this is device 2. And this is the Intel CPU. Let's put the PTX just to have different backends. And that's all you need to do. So if we recompile the application and run, so let's do that. Let's do Maven clean package. Okay. And we run the application. We run with Tornado. This is how we run this application. It's also described over here in case you want to follow along. So let's go back. I'm gonna run 3 iterations. Okay, so it's gonna run 3 times the same task graph. Remember, each task graph is composed of 4 tasks. So we're gonna see 4, 4, and 4, right? That's the goal for the experiment. I'm gonna enable debugging information just to see where the code is executed. So I'm gonna run with thread info and let's run it. Let's see what happens. So I'm gonna make this bigger. Okay, so let's go from the beginning. So we start with the first task. We select, let's put this side by side. So we select here device 0. Device 0 is PV for the black and white. So let's go back to the first message here. So this is PV, okay, for the black and white Intel integrated graphics. Great. The second task is the blue red, okay, and we select device 1, which is the RTX 3070 with OpenCL. Blue red, RTX 3070 with OpenCL. Awesome. The next one, we select the blue green for device 2 is Intel integrated graphics with OpenCL. Let's see. Blue green, Intel integrated graphics with OpenCL. Awesome. And the last one, PTX, okay, is device 20, device 4, okay, is blue RTX 3070 GPU. Amazing. So we run the same, so one task graph, each task map to a different device. That's great. However, and then we see the total time is 2 seconds to process this image. Okay, just one more thing out of curiosity. If you're curious about the output of this, let me show you. So I'm gonna bring this. So the output generates 2 images. One is blur, you can see it's a bit blurry, and the second image is black and white. And the input images are stored here. So that's the original one. Okay, it's very sharp, as we can see. Right. So far, what we have done, though, is to run each task on a different device, but this runs sequentially. What do I mean by sequentially? It means that Tornado runs first the first task. When it finishes, launches the second task. When it finishes, launches the third task. The task itself, by the way, is running parallel. and that's the number of threads that we're running. But the tasks are run sequentially, right? The dependency between them. But that's not what we want. We want to go a step further and run concurrently. How do we do that? Well, TornadoVM 1.0 has a call called with concurrent devices. Okay, let me put this over here. And if I do that and recompile again and run, now it's running with concurrent devices. So basically the order is unpredictable. Okay, it's not deterministic. Because what it does is TornadoVM spawns a set of Java threads under the hoods. Each Java thread handles the execution for a different task. So we might not see the same ordering. Let's see. So we go to the beginning. Oh, sorry. We go to the beginning. Over here, we see that it's blur effect, but actually the first one, what we call was black and white, right? So it's affecting the ordering. So if you want to go deep about this, there is a flag that is called print bytecode. Print bytecode or print bytecode? I can't remember. Let's see, print bytecode. Yes, print bytecode. Okay. So what it does is that it prints the internal logic for dispatching the code with Tornado. It's very low level. We don't have to go to that detail, but what I want to show is the ability of this multi-threaded, because it runs, for example, here from pool 1 thread 1 is running on integrated graphics. Pool 1 thread 4 is running on the PTX RTX 3070 with the PTX backend, and so on and so forth, right? If we disable concurrent devices, so we go back, we execute this, we recompile the application. And then we run it with the print bytecode information. Okay, now we see that it's running again in order and it's running from the main thread, right? There is now multi-threaded inside. So, okay, that's awesome. So now what we could do then is to play with different, let me go back to the task graph definition, with different values here to increase performance. But before touching performance, let's run all of them and see the analysis just by selecting each one individually. So I already execute that before recording this video. So I'm gonna show you the rounds of experiments, the performance. So I'm running the image I showed you is this amount of pixels, 5,000 pixels by 4,000 pixels. And the report is the speed up and is in the average of 99 executions. So I run 100 times and I discard the first execution because the first execution, the JIT compiling in the case of TornadoVM is invoked. So I just run the, after the JIT compilation, and I compare against Java sequential. And here I show you different versions. One version running with Java multi-threaded, so no Tornado in it. The second with Tornado and selecting for all tasks the OpenCL CPU. The next one, all tasks running on the Intel integrated graphics using the SPV backend. Then all of them running on the RTX 3070 GPU with a PTX backend, and finally with OpenCL backend on the same GPU. And that's a speed up, so the higher the better. So as we can see, running with OpenCL, RTX 3070 with OpenCL, you can get more than 500x performance compared to Java. If we compare against Java multi-threaded, which is the best parallel version you can get out of the box with Java without any external dependencies, we see this picture over here. So now the baseline is Java multi-threaded. Again, the higher the better. And I show you for the OpenCL, for the SPV, for the PTX running on the big GPU, they're 3070 and the 3070 with OpenCL. So we see that even running Tornado on CPU gives you almost 20% faster than Java multi-threaded. this is because we're using a different compiler. It's a domain-specific compiler and can apply better optimizations for CPU. So if you have a data parallel application and can be expressed with OpenCL, you're gonna get a bit higher speedups by using OpenCL, which is quite interesting. If we use the integrated graphics with SPV, you get almost 60% speed up against Java multi-threaded Java streams. And obviously the big GPU, this task, okay, this image processing is made for big GPUs. You can get a very high speed ups. But now the question is, okay, if I want to mix with different combinations to increase performance, which combination should I pick? And that really depends. To analyze this, we should look at the profiler, because just by looking at these numbers, I will say there is no need to jump to select different devices. Select the best one, because the performance gap between this one and the rest is so big. However, if we enable the profiler, we might see something different. Let's do that. Let's do that. So let me go back to the IDE. And let's run everything on the best device. Let's say on the RTX 3070 with OpenCL, which is what was the best one for us. So if we select that, and then we recompile the application, and then we run, we are gonna disable thread info and the print bytecode. I'm gonna enable is the profiler. So I'm gonna enable the profiler, and I'm gonna print console. And that will dump a JSON entry after every execution. Remember, we're running the application 3 times. We will increase the number of iterations later. By the way, when I measure, I put 100 here, okay? This is just for this demo. So if I run it with the profiling information on, I'm gonna get a JSON entry afterwards. There we go. So let me see what happened. Oh, I choose the wrong device. Sorry. I choose the wrong device. So let's go back, because I'm interested to show you the execution on this one with the best. It's device 1. Let's go back. Let's recompile and run again. There we go. So let's wait for the profiler. There it is. So let's take a look. I'm not gonna pick the first iteration because JIT compilation is involved. I'm gonna pick the second or third iteration. So let's go to the end of the execution. By the way, this is the total time that processed that image is 0.2 seconds, okay? If you're curious, the sequential application took around 92 seconds to process. Right, so by looking at the profiler, what do we get here? We get an entry per task, and this is the pure GPU kernel time in nanoseconds. So for the blur filter, this is the amount of nanoseconds. So blur channel, red channel, and blue channel. So green, red, and blue. We see that time kind of is around 38 milliseconds, I think. It's very fast, but it's consistent across the different tasks for the blur effect. That makes sense because the computation is the same, just changing data. However, if we look at the black and white, the kernel time is so fast. That means that we have to send a lot of data to the GPU just to process a very simple kernel. So because the performance gap, if I go back to the graph, performance graph, over here, sorry. If I look at this performance graph, the performance gap between the best device and the rest is so big, I'm gonna focus on changing the device or try to alter the device for the task that it differs quite a lot, which is the black and white. So what we can do then is to run that one on a different device. and measure performance. So let's do that. So just to establish the baseline, I'm gonna increase the number of iterations. So let me increase the font as well. Right, I'm gonna increase this to 100 iterations, okay? And I'm gonna process this concurrently with concurrent devices. Okay, keep in mind we need to enable this, and I'm gonna run on the device 1. Okay, all of them. So let's recompile the application and run. So it's gonna run 100 times. And I have a table to compute the average. So keep in mind that I'm recording this in the same machine I'm running the experiment, so times might differ quite a lot. But at the end of the presentation, I'm going to show you the performance I got offline, just to be more precise. So let's wait until the execution is finished. We copy all of these, and I have a table, a spreadsheet to compute all these numbers. So I'm gonna put this in the baseline part, and I'm gonna process the average of the last 99 numbers. Okay, 99 execution, and I discard the first one because it's the JIT compilation. As you can see, the time is a bit higher, right? So I don't want that. Let's focus on the pure numbers after the JIT compilation is done. So this is the amount of nanoseconds. It's around 0.2 seconds. So let's run now with the combination in which I execute this on the integrity graphics. Let's pick SPV, so it's device 0. So let's do that, device 0, the rest device 1. And if I do that and recompile, let's do that. And run again. Right, I can already see it's a bit faster than the previous one. Let's see. So we wait until the execution finish completely to measure exactly the same way. Again, keep in mind that I'm recording this video in the same machine I'm running benchmarking. You shouldn't do that if you run benchmarking. This is just to show you the potential. Okay. So if I process that and I compute the average of the last 99 execution, I get 2.4% improvement. Okay, it's something. The thing is, I already got something better, a bit better, but it's better than the fastest configuration, the fastest static configuration that I thought would be. Let's do one more experiment. What if we select the GPU again, the 3070, but using the PTX backend? Let's do that. So if I do clean and run, okay, we wait until all executions are finished to compare the same way. It's almost done. There we go. So we copy the new numbers over here and we insert it there. Press OK. Now let's see the difference between them. So that's the average, okay, for the new ones. That's the average for our baseline, and this is the speed up between the two. So it's the computation, this one divided by this one, and it's 3.5%. So it's a bit faster even. So we go from I can't remember what was 2.5 or 2.4 to 3.5%. That's awesome. Right, and that's how you can use, you can exploit concurrency and multi-device with Tornado. As you can see, it's very easy. You get the device using the factory method and set it with this method from the execution plan. Now, I'm gonna show you the results that I process before the video in a clean environment. So the baseline is everything running with the OpenCL RTX 3070, which is the fastest single device. And I'm trying to beat this combination. So if I process the black and white with the integrated GPU, the first experiment we did right now, I get 3% faster. If I process the black and white with the RTX backend instead, I get 4% faster, 4 point something actually. So that's great. That's awesome. That's how you get, to play with different combinations.
So with that, I conclude this video. I have shown you different combinations in which you can get an increased performance. And yeah, let me know in the comments down below if you play with this exercise, what's the best combination for you, and if you found a better combination. So with that, happy coding and see you soon.